Okay, sounds good. Welcome back after I don't know, like an extremely long break for a variety of reasons. And it seems like we are going to have more and more breaks because of either holidays or people getting married and whatnot. So yeah, so we'll figure out some way to make up for the lost lectures, etc. But so today is going to be like a continuation of something we saw like a few weeks back. Hopefully I will recap the thing, but in my opinion, today's lecture is something that you don't really need to know those things. I mean, it would be great if you remember or recall the precise reason why we came to the problem that we're going to solve today. But independently, I think it's a fantastic algorithm that I think people should know. Okay. So today's lecture is the main focus is going to be on this LLL algorithm by Lenstra-Lenstra-Lovasz, which is an approximation algorithm for solving a very important problem called the shortest vector problem in a lattice. It's often called SVP. And the LLL algorithm provides one approximation algorithm. It's an efficient approximation algorithm with some approximation guarantee. And the SVP is a problem where I really can't, it's absolutely important for various modern cryptographic primitives and so on. But there often you deal with the hardness of the problem where the approximation ratio is much better than what LLL provides. But it's good to know algorithms like LLL because it's a very surprising algorithm and the tools are very simple. These are mostly things that you might have seen in your undergrad or something, and it's just putting together the tools in a really clever way. Okay. So before we go into it, considering that we've had such a long break from last time, I just want to recap where lattices, etc., fit in the discussion that we have been having so far. And once I do that, I'll just move to the problem on lattices and we'll just try and solve the problem. Okay. So what we were doing was we were trying to come up with factorization algorithms for polynomials where the coefficients were integers. To make life simple, let's just say that somebody provided you a monic polynomial, by which I mean that the highest degree term is 1. The coefficient of the highest degree term is 1. But I also tell you that all the other coefficients are not too large. So in the sense that it requires C bits or roughly C bits to tell you what the coefficients are. And in absolute value, it just means that all the integers for the other coefficients are somewhere between -2 per C and 2 per C. So there's some integers of that type. So therefore, we are interested in a running time where I want to run in polynomial time in C and whatever is the degree of the polynomial, because that's roughly what my input length is. Because to specify a polynomial, I need to tell you roughly degree plus 1 coefficients. And each coefficient I can now specify using something like C plus 1 bit for the sign or something. So some such thing like that. Okay. So, and the algorithm that we saw, or rather we outlined last time, was this thing of it's like a very, how do I put it? It's a very natural generalization of what we did in the bivariate setting. Like each block by itself is almost exactly like what we did in the bivariate setting, except the role that is played by the variable y in the bivariate setting is now going to be played by a prime p. So that's mostly the difference. And in fact, it's because this p is a prime and not a formal variable, one needs to rephrase certain things slightly differently. Okay, so the first step, which is often a pre-processing step, which is like you somehow want to say that without loss of generality, I might as well assume that f has certain properties. So those are some easy corner cases that you deal with. So you assume that f is square free, because if it was not square free, you just take the GCD with its derivative, and then you're done. Okay, and secondly, you also want to make sure that f remains square free when you consider it modulo p. And since we have dealt with the resultant for so long, etc., this basically will amount to saying, look at the resultant of f and its derivative, which is a number. Okay, and now you just want to make sure that if the number was non-zero, I want it to remain non-zero even when I go modulo p. So all you're saying is find a prime p that does not divide this number. So we'll do something stupid. We'll just try the first few primes. Okay, and just find the first prime that does not divide this result. Okay, so that's what, so that is the prime p that we are going to now stick with, because now you are in a situation where you're dealing with a polynomial f such that f remains square free even modulo the prime p. So now f mod p is like, it's like you're trying to factorize f over the finite field fp, which we know how to do. So therefore, we will run our factorization algorithm to get g naught and h naught, where g naught is one of the irreducible factors and h naught is everything else. Again, something I have not written here, but if this process already tells you that f is irreducible mod p, then of course you just say it is irreducible. Okay, because if f factorizes over the integers, of course it should, the same factorization when you just reduce modulo p should hold over the finite field. So if you know it's irreducible in the finite field, you know it is irreducible over. So you can return that. But otherwise, you have something to start with. So once you have this, what you do is you do this Hensel lifting process, where the ideal is now going to, instead of the ideal being generated by y, it's now generated by the prime p. So therefore, you will get p power 2 power k. Okay. Again, for k large enough, last time we actually saw precisely what this large enough was. It was some function of this 2 power c and n and so on. So the number of steps that you will have to do this will be polynomial in the sort of parameters you're interested in. Okay. And here came the reconstruction step, which is we want to find, basically solve this equation. We want to find a g tilde such that g tilde is something I can obtain by multiplying this gk, whatever is the lift we have got so far, by some polynomial, such that mod p power 2 power k, g tilde's coefficients look very small. That is, even though gk could have horrendous coefficients, somehow there is a way of multiplying it with some other polynomial, such that suddenly now g tilde looks very reasonable. It looks like a factor of f. Okay. And that we basically phrased it as saying, what is this saying? It's like saying, is there some integer linear combination of gk of x, x times gk of x, x squared times gk of x, etc., etc. And then maybe you cancel off all this p power 2 power k business because you're going mod p power 2 power k. Is there some suitable integer combination of these vectors that results in a short vector g tilde? Okay. And this is the shortest vector problem in the, or not the shortest vector problem in the lattice. We are trying to find a short enough vector in this lattice. Okay. And the thing was, we basically said that if the g tilde we found using whatever algorithm we are going to do today, if the algorithm returned something which was very bad, like the size of g tilde was just too large, and you know this looks nothing like a factor of f, then you already return irreducible. Otherwise, it somehow happens that GCD of f and g tilde will always be non-trivial and it will give you a factor. And this was based on analyzing the resultant of f and g tilde and showing that that as an integer is smaller than p power 2 power k, if you recall what we did in the previous thing. So this was roughly where it fit in, where lattices, etc. fit in the the univariate factorization over integers. And today what we are going to focus on is just this. We are going to abstract out everything else and just deal with the following problem, where somebody gives us a basis for a potential lattice and asks, give me a short enough vector in this basis. Okay, and that's the problem that we are going to solve. So that's the main task for today. We are given a basis for this lattice, let's say B1 through Bm, and they're all present in Z to the n. For simplicity, I will just assume that m equals n. Okay, so that I don't have to deal with two separate letters and I'll always keep getting confused as to which is what and so on. But so you're given some lattice and you want to find a short enough vector in this lattice. Okay, and the goal, what today we'll do is like we will get 2 to the n approximation for this. By that, what I mean is if the shortest vector has length L, shortest non-zero vector has length L, I will give you a vector that is no longer than 2 power n times n. Okay. On the face of it, the moment you see a factor like 2 power n, it just feels like a terrible, terrible factor. But I do want to somehow maybe spend a couple of moments to tell you that this is already very non-trivial because it doesn't say anything about how long the basis vectors originally were. Like the bit complexities of the basis vectors appear to be completely irrelevant to this. And it only cares about the dimension of the space. And it's that makes this extremely non-trivial. So let me give you an example. So I have a bunch, I give you a basis, I give you a lattice here. Okay, what's the shortest vector in this lattice? How do you go about solving this problem? Okay, so one thing is you can try to plot these two vectors and see what sort of lattice it generates and hope for this. So if you plot both of these vectors, it look like some extremely skewed vectors that are pointed in one direction or something. Okay, so but suppose I actually told you that okay, the lattice that this thing ends up generating, this is actually the more familiar integer lattice. Doesn't look like that at all, right? But turns out if you think about it more, okay, it turns out that you basically get all possible integer points in this lattice. In fact, the lattice is exactly that. So therefore, the shortest vector is just E1 or E2, like the standard elementary basis vectors. So and notice, and I'll basically try and convince you that I can set up such that the numbers here can be like ridiculously large. Okay, but nevertheless, we can always do something of this. So, okay, maybe let me give an example as to why is this the case. Well, why is it the case that the lattice is equal to C2? Okay, so so suppose now that you know that the lattice is equal to C2, that is, someone has given you this hint. How would you prove this? Okay, so let's just try to do the most obvious thing. Okay, so this is 37 and 7, and this is 90 and 17. Suppose I want to be able to construct E1 and E2 according to this, by this. What should I ensure? I should somehow make sure that this vector is some integer combination of these two vectors. I need to show there exists some integer combination such that that works. Similarly, this vector is supposed to be some other integer combination of these two vectors. Okay, so what you're really looking for is you want to know, is there a matrix I can put here? A1, A2 and B1, B2. Sorry, I should probably have written A1, A2 and B1, B2 to mean that this particular integer combination of these two vectors yields this vector, and this particular combination of these two vectors yields this vector. And more importantly, I want all of these 4 entries to be integers. Okay, now you can ask yourself, if there is a matrix such that this times this matrix equals the identity matrix, what is the only choice that this matrix can be?
Inverse.
Yeah, so therefore, if this matrix is A, this better be A inverse. Okay, and now you ask yourself, when will it be the case that you have a lattice, and therefore that you can just list down the vectors and put it in a matrix and call it some matrix A? When will its inverse also be an integer matrix? That is, we are asking, when is inverse of A an integer matrix?
If the data divisibles I forgot the terminology that we do for A inverse.
Sorry, what?
So A inverse is something, a matrix by data, right?
Good, excellent. So,
I forgot the name of the matrix.
No, it doesn't matter. You don't need to know the name of the matrix, but let's just take determinant on both sides. What do we end up getting?
Determinant of A.
Determinant of A times determinant of A inverse. But for now, let's just assume that this is A and this is B. This is an integer matrix. This is some other integer matrix. So their determinants will also be integers.
So basically it will be either +1 or -1.
Exactly. So this basically the only way this can happen is if determinant of A equals +or -1. In fact, the whole thing is an if and only if because of exactly what Saurav said, which is that if you remember your whatever the inverse formula from undergrad or something, it's this: you look at the adjoint of A divided by the determinant of A, and as long as you're not dividing by something that is crazy, you will still get integer coefficients. So all I had done was I arranged for it in such a way that 37 times 17 is, I think, 639 or 629 or something like that. So basically it's one less than this thing. So I just arranged for a matrix such that the determinant was plus or minus 1. So obviously you can also arrange for some random long vectors such that the determinant is plus minus 1. So you're somehow hiding the fact that you are actually working with the natural integer lattice. Instead of doing that, you are just dealing with some complicated expression. So hopefully there's some sense that the fact that you can come up with an approximation value that does not depend on the sizes of these numbers at all is quite remarkable. Because I mean, it feels like I can hide my integer lattice somewhere by doing one of this nonsense. And somehow any algorithm that manages to do a good enough approximation of the shortest vector problem must figure out a way of somehow unentangling the situation.
But as if we increase the size of the matrix in process, finding the determinant is also getting hard, right?
That's right. So I agree. But the thing is, in general, you have time to run proportional to the bit complexities involved. So all I'm trying to say at this point is that there are ways in which I can make the shortest vector substantially smaller than the vectors I gave. And not just, I mean, like this question might still make sense even in a 2x2 setup. That's what I'm trying to say.
No, I am saying that if we have a n cross n matrix and we are looking a lattice in n dimensional, so is it there might be a sufficient condition that if we look in a sub matrix or sub principal matrix where determinant is plus or minus 1, will that be enough?
No, I don't have a concrete counter example, but because I'll show you. Maybe let's revisit this after we see the algorithm today, because there are steps of the algorithm which are very, very crucial. So it's not as simple as finding a submatrix that has a certain this thing.
Yeah, obviously submatrix should be some. There will be some criteria to finding the order of the submatrix. It's not like if we find any 2x2 submatrix whose determinant is minus or plus 1, your result.
No. So, but the point is, I mean, this particular thing of the determinant being 1 or minus 1 is often helpful to tell you whether your lattice is actually the integer lattice or not. But maybe your lattice is not the integer lattice. Somebody could have provided you a lattice where it just so happens that one of the vectors there is quite short, but there are plenty of other things which are like horrendously long. And we are just trying to find, the short vector. If all we wanted to test was, does the lattice correspond to the integer lattice? Then I've given you an if and only if statement. Just compute the determinant. If the determinant is plus 1 minus 1, it's the integer lattice. Otherwise, it's not. Okay. So, but the point is, it's often not this simple. So, because the problem we are trying to solve is a bit more general. We are not given any promise that the lattice is actually an integer lattice. Okay. But let's ask ourselves the following question. Even if the lattice was the integer lattice, how are we suddenly so sure that E1 is the shortest vector? I know I'm being a little facetious here, but the integer lattice has a specific extra property that makes it very clear that, the E1 or E2 must be the shortest vectors. Nothing else can be the shortest.
Sorry to interrupt. Shortest vector in the sense distance from the zero origin?
Distance from the origin. Just take L2 norm. Okay. Okay. And it's a stupid thing to say, which is that it so happens that once you go to the integer lattice and you have a basis which is E1 and E2, it's not just any basis, it's an orthogonal basis. Okay. And because of this, Pythagoras theorem will basically say that if something is a linear combination of E1 and E2, well, it has to be at least as large as E1 or E2. Which is not true if your vectors are sort of skewed and so on.
Can you argue in the way that so the determinant will be for an integer matrix? Determinant will be rational only the integers, right? Among the z.
Yeah, that's right.
Z, right. So if we just consider the concentric circles of radius r belongs to z. So for the lowest one we have only 0 or 1. If we are looking for invertible matrix, it will be 1. So in the circle of in S1 only the 4 lattice points are there. So E1 and
no, but I am given a specific lattice, right? I mean, like for instance, I don't know of a quick way of figuring out what are all lattice points of distance 5 from here? I mean, I don't even know if there exist any, I mean, on the face of it. And in fact, that's the problem. I mean, the thing is, I mean, I don't seem to have a good way of figuring out, is there any vector of length at most 5 that's present in this lattice?
Okay.
Okay. And in fact, this problem in general is hard, because if I can answer this problem for any choice of this, whatever the number 5 that I chose, then you are literally solving the shortest vector problem, or at least a decision version of it. You are basically saying, is there a vector in this lattice of length at most a given parameter k? And now this problem is super hard. This problem is NP hard. Okay. So, but what we are going to do is we are going to get a short enough vector. Okay. So all this I was trying to somehow get to the fact that if the basis vectors happens to be orthogonal, then the problem is actually much easier. Okay. And here is a simple claim. Okay. If the basis that was provided to you was orthogonal, it doesn't have to be E1 and E2. It could be any bunch of vectors. But suppose I gave you an orthogonal basis. By orthogonal, I just mean the pairwise every dot product is 0. Okay. Then the shortest basis vector is actually the shortest vector in the lattice. Okay. And I mean, the proof is trivial, but I'm still going to do the proof because soon there'll be a modification of this which will start showing. So suppose there is some vector B opt, which is the smallest vector in the lattice. The very fact that it must be in the basis basically means that you can write this as summation alpha I bi, where each of these alpha i's are integers. Okay, and since B opt is a non-zero vector, not all the alpha i's are equal to 0. Okay, so what does this say about B opt squared? By Pythagoras theorem, this is exactly equal to alpha I, I mean summation alpha I squared mod bi squared. Okay, now so let's just pick one such alpha I that shows up, which is non-zero in this equation. So this is at least as large as alpha I squared mod of bi squared. Okay, and here is where I'm going to use the fact that alpha i's were integers to say that this is at least as large as mod bi squared. Okay, so we've used both. We've used the fact that not all alpha i's are equal to 0, and also the fact that alpha i's are integers to say that whatever is your optimal, it's at least as large as one of my basis vectors. So certainly the smallest basis vector has to be one of the lattice points, or one of the, sorry, smallest lattice vector must be one of the basis vectors. Okay, so the first order approximation of what we are going to do in this algorithm is that you're going to try and make the basis orthogonal as possible. You're going to basically say the hard cases that I told you about, where things were, vectors were like no skewed and pointed in one direction. And they're going to somehow unskew them as much as possible and hope that at some point we will have enough confidence to basically just output one of the basis vectors and say that that must already be good enough. Okay. And to do this, we're going to revisit something that hopefully you have seen in either your undergrad or maybe in some other context or something, which is called the Gram-Schmidt orthogonalization. Just wanted to maybe take a quick this thing. I mean, are there people who had not seen Gram-Schmidt before? I gave some quizzes in the morning. Okay, but basically Gram-Schmidt is just a way of saying somebody gives you a basis or some bunch of vectors u1 through un, and the idea is to build a different basis v1 through vn such that they span the same space but are now orthogonal to each other. And you just do this in the most systematic way possible. Okay, and it's a very natural, I mean, it's one of those just do it proofs. I mean, you do the one thing that you can and you just make sure that you're doing it in some systematic way. Okay, so the idea is going to be, it's an iterative process where it takes one vector at a time and then keeps returning one of the Gram-Schmidt vectors. It will slowly keep making your basis orthogonal at every step. Okay, with the property that if I've read the first I vectors, then the first I vectors I've outputted so far, they still span the same space, but now are orthogonal. So that's the invariant you're going to keep maintaining. That is, you don't span something outrageous. Okay. So what do you do? So what should V1 be equal to? Well, at this point, we don't know anything better. So you might as well make it equal to U1. Okay. And now the point is, what should V2 be equal to? So you basically tell yourself, look, I want it to span the same space as U2, or rather, I want V1 and V2 together to span the same space as U1 and U2. So I can afford to add some, I don't know, some alpha times V1. Because this way I'm not changing any, the space spanned by V1 and V2 is the same thing as the space spanned by U1 and U2. And now it's just a question of what should I choose this alpha? Okay, and now you ask yourself, what constraints do I have? I am told that V2 must be orthogonal to V1. So let's just take the dot product on both sides and see what we get. So this implies that V2, V1, what will I get here? I will basically get U2 times V1 minus alpha times V1 times V1. And I want to make sure this is equal to 0. So you basically set alpha to be equal to U2 V1 divided by V1 V1. Okay, so therefore this will, I'm just erasing this and I'm just going to write this here, minus U2 V1 divided by V1 V1 times V1. Is this okay so far? Okay, so now what do we do for V3? Again, I want to write this as U3 minus some alpha times V2 minus beta times V1. So that I still end up spanning U1, U2, U3. And I just need to set up what alpha and beta must be in order to make sure that V3's dot product with V2 is 0 and V3's dot product with V1 is 0. Okay. And I trust that you would have tried this out during the morning quiz. And this will basically tell you that this has to be minus U3 V2 by V2 V2 times V2. And this is U3 V1 by V1 V1 times V1. Okay. And this is just one of these, I mean, like if you just repeat this process, this is exactly what you are going to end up getting. Okay. Are there any questions so far in general? Okay. So in general, what is going to happen is that VI.
Sir, this is physiotherapy TI, right?
Sorry?
Yeah. मेरा एक अपॉइंटमेंट लिखाना था कल का नेत्रा मैम के पास.
Sorry.
Yeah, I just muted. Okay. So in general, VI is going to be UI minus terms that look like J going from 1 through I minus 1. That is, this will involve all the previous VIs. And let me just write this as mu I comma J of Vj. Okay, where the mu I comma J is some constant. What is mu I comma J going to be? I mean, if you recall the previous this thing, so this is going to be UI Vj divided by Vj.
So I guess the naive question would be, if we are now working with integer lattices, so
Excellent.
it's just taking the closest integer or something.
Good. That's what we are going to do. Okay, we are jumping ahead a little bit, but that's precisely what we are going to soon end up doing. Okay, but nevertheless, this is going to give us some, I mean, this is the standard Gram-Schmidt orthogonalization. If you don't care about the fact that these mu's are currently rational numbers. Okay, if you're okay with, I mean, I'm not really dealing with lattices, I'm dealing with vectors or something, then this is a perfectly legitimate way of orthogonalizing a certain basis. But at this point, it will be useful to get a sense of what exactly is going on here. What is Gramschmidt doing? Okay, so to begin with, I had a vector space which was maybe spanned by this thing. Now the next, so this was equal to U1, which I decided to call V1. Now I got a new vector, and this was some U2. And what we said is basically the following. We said, look, this is the space that I'm currently spanning. U2 appears to be giving me some new components, but there is part of the component that's already in the space I am in currently. So what I want to do is I want to get rid of the component of U2 that is in this space. And I only want to take the orthogonal component. Okay. So what we did was, this is what we said was V2. Okay. And now this is our space that we currently have. Now imagine a third vector coming in. And we basically say, I don't care about this vector in its entirety. I only care about what is the orthogonal component of this vector with respect to the space that I currently am in. So in some sense, each Vi is the component of Ui that is orthogonal to whatever the span of U1 through Ui minus 1. Okay. The reason I'm saying this in this way is because if you care about specifically what the ith vector is, the only thing you should care about is the span of everything before that and not the individual vectors that are involved. So if you had come up with a different set of vectors such that the span is the same, that would not have changed the ith vector, because every step in the Gram-Schmidt orthogonalization, the only thing it is doing is it's basically saying, okay, I have a certain space currently. You have given me a new vector. What is the orthogonal component of this vector? You don't particularly care about what the space was spanned by to begin with. Okay. Hopefully this will enlighten a little bit about one of the quiz questions that was there on the catalog. Okay, but we'll get to that. Okay. So in general, let me just write down Gramschmidt. So V1 is equal to U1. I'm going to write this a little differently. So V2 plus whatever, mu2 1 V1, this is equal to U2. I mean, I'm just moving this guy to this side. I'm putting all the V's on one side and U's on the other, etc., etc. And this in general is going to be Vn plus mu n minus 1 Vn minus 1 plus blah, 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 plus mu n1 V1. This is equal to U1. Okay. If
question.
Yeah.
So are we going to guarantee that sum of this lower triangular matrix that we have integer value matrix?
No, it need not be integer values, but we're going to get as close to it as possible. I'll soon get to that. Yeah, just hold on for a little bit, but you're right. I mean, we'll try to do something very similar. Okay. So, I mean, like Saurav just mentioned, if you look at this equation that Gram-Schmidt satisfies, it basically can be written in a matrix form, where you're saying, if I think of V1 through Vn as written up as rows of a matrix, which is what you get after you apply Gram-Schmidt, and if U1 through Un is written as the rows of the matrix, which is your original basis vectors, then all that we are saying right now is that there is a way of writing U1 through Un as some lower triangular matrix times V1 through Vn. And it's a very special sort of lower triangular matrix. It has ones on the diagonal, and it then is basically it's made up of a lower triangular part, which are these constants mu's that showed up in the expression for Gram-Schmidt. And in fact, you can basically say Gram-Schmidt, you can rephrase it in the following way. Can you write your matrix as a lower triangular matrix with ones on the diagonal times an orthogonal matrix? There is a unique way of doing this, and that's what Gram-Schmidt gives you. Okay, so this is what Gram-Schmidt orthogonalization is at this point. Yeah. Okay. Now, as I mentioned earlier, one way to like sort of reinterpret Gram-Schmidt geometrically is that you're basically somehow always guaranteeing that at any prefix you are spanning the same space. That is, span of V1 through Vi equals span of U1 through Ui. This is true for all I. And furthermore, Vi plus 1 is basically the component of Ui plus 1 on the orthogonal space. Okay, so let's get to the question that, sorry, go ahead, Sarah.
Yeah. So this is a matrix of the form A V equals to U, capital A, U.
That's right.
Okay. So, and this is invertible also.
That's
so
right.
If we just look at A V equals to A inverse B, A inverse U, V equals to.
By the way, so just to make sure that we stick with the notation, I will start calling this matrix as M because it involves these mu's.
Okay.
And capital mu in Greek is just M. Okay. So we currently have something that looks like MV equals U.
Yes. So my point is that we can write M as I plus some matrix, right?
That's right.
And if that other matrix is a nilpotent matrix, then
that other matrix will always be nilpotent.
Nilpotent. Okay. So when you am taking the n inverse, and if I apply some same matrix of the form so that the diagonal part goes to, off diagonal part goes to 0, then we are achieving integer valued matrix, right? Solution.
No. Sorry. What do you mean?
So M V equals to U. So we can write V equals to M inverse U.
Okay.
And now I am trying to apply the inverse again and again, so that.
So what do you mean by you're applying it again and again?
On the both side, M inverse. Means Gramschmidt process is a single process, right? To get a orthogonal basis vector, right?
Yeah, but once you get an orthogonal basis vector and you apply Gram-Schmidt, nothing will change. The basis won't even change.
So now we have to apply a rotation vector to get integer value. Rotational matrix, right?
No, I mean, what I don't understand is, right now the vectors in V are no longer in my lattice. Yeah. Because these mu's involve some various fractions.
We got the vectors V1 to Vn in some circle. Okay. But I don't know whether it is projecting on the lattice point or not. So what I am trying to do, I am trying to rotate them in an angle so that they try to point nearest to the lattice point.
No, but again, that rotation also needs to be an integer valued and so on, right?
We are trying to find that rotation, right?
No. So firstly, it may not be the case that the lattice I have in question, there may be no orthogonal basis for this lattice at all. It may just be that there is no way of coming up with an orthogonal basis for the same lattice. So that's already a problem. So, but this is just a means of trying to get close to a short enough vector. Okay, so Gram-Schmidt is going to be our guide for us, but it's not the final answer. We are not going to somehow figure out a way where the Gram-Schmidt vectors will be lattice vectors and we are done. No, it's going to be a little bit more complicated. Okay, hold on to this thing, and maybe at the end of it, if you feel like
sure.
Okay, so the question is, can we do this on lattices? The problem is not quite as these mu ij's are rational, and very likely they're not integers because you're dividing by various these. And as I just mentioned, there are examples where it's not quite you may not ever be able to do this completely. Okay, but what we are going to try and do is trying to get as close to this as possible. Let's do as much of let's make it as close to integers as possible, and somehow hope that this gives us some information. Okay, and this is called the rounded Gram-Schmidt process, but I'm just going to do this by an example and hope that should be clear for people. Okay, so here is the goal. So this is B1 star, B2 star, B3 star. So I basically noticed that there is a 2.8 here. Okay, and I want to round it off as much as possible. Okay. So what I will do is I will apply like a matrix on both sides of this equation in the hope that this 2.8 becomes a smaller number. Okay, so you try and do row operations because that's what multiplying on the left corresponds to. So that all of these integers that, I mean, whatever these entries that you have are as small in absolute value as possible. Okay, so this is some heuristic that we are going to do. So what I'm going to do is what would happen if I just had the vectors b1, b2, and I basically had b3 minus 3b1. Okay, because there was a 2.8 here, and if I wanted to cancel it off, I need to replace row 3 by row 3 minus 3 times or 2.8 times row 1. That's what I would have liked to do, but 2.8 is something I can't afford. So I'm going to get the closest next thing, okay, which is 3. So what would happen to this matrix? So this will now become 1, 1, 1. This will become minus 0.2. Okay, and this will become something like, what will this be? I don't know, something like minus 6.3, I guess. And then 4.1. Right? Let's next fix this value. What should I do now?
Add 6 times the second term.
Okay, so if I add 6 times b2, okay, and now what happens is this thing will now become minus 0.3. We're just doing row operations to somehow make this fractions somehow manageable. And then finally, the last thing is going to be, I'm just going to replace b2 minus 4 times b1. Okay, and that is going to make this entry as 0.1. Okay, so what has happened is that the Gram-Schmidt vectors didn't change. Okay, but I have now changed my basis from an original b1, b2, b3 to something that almost looks like you applying the Gram-Schmidt operation, but you didn't apply it fully. Right? You sort of, you got to a point where now you are something like, okay, this vector and this vector aren't quite orthogonal, but the pairwise dot products don't happen to be too large. That's the sort of setup you have come up with. Okay, and I will just call this a rounded Gram-Schmidt, by which I mean is that it's a way of writing some matrix M times the Gram-Schmidt vector equals your new basis, such that all off-diagonal entries are between plus half and minus half, because that's the best I can achieve. If I'm only allowed to do integer combinations, then the best I can get to is like plus half and minus half. Okay, so here's what we are going to do. We are going to find the actual Gram-Schmidt.
I didn't get one part.
Yeah.
So given any bound, can we make it close to means not plus up 1 by 2 to the power n to 1 minus?
No,
1.
I don't know how to do this, because the closest, I mean, if this was like a 2.5, I mean, either I subtract 3 times or I subtract 2 times. So I'll be left with a 0.5 slack one way or the other. Okay, so this 0.5 is only because any rational number is within 0.5 of an integer. That's all. And I don't know how to make this better than 0.5.
Just a small confusion. No, the last row we did screens lower tab is obstructing. So
okay.
yeah, so I mean b3 minus 3b1 first took care of the 2.8.
It took care of this entry, but it might
the 6b2 can now will add up this some 24.
Sorry. Okay, so then maybe I should have done it in a slightly different order, I guess. Okay, let's just
like first deal with the second row.
Yeah, I think that's what we should have done. So 4.1, 2.8 and minus 3.3. Thank you. So first let me deal with this guy. Okay, so for this I would have done b3 minus 3b2.
Yep,
okay, sorry.
Yes, you can use the only b1 vector. That will be easier to substitute.
No. The what Varun's point was quite valid. So the point is, if I replace b3 with b3 minus 3b2, one thing that I end up is that this is going to become minus 0.3. But the problem is so will this entry. This entry will change. Right? So this will become, I don't know, 2.8 minus 3 times 4.1. 12.3 minus 2.8. What is this? So this is apparently minus 9.5. So you will end up with something that looks like minus 9.5.
But the ideal way to do is that first just use the first row to reduce the second row, and then use the second row to reduce the third
No,
row.
the point is that the errors will always compound. The right thing to do is start from the last entry and start from the rightmost entry and keep fixing it like this. I mean, that's the only systematic way to do things. Okay, so this will become minus 0.3. And now I actually subtract whatever 9 times row 1 from this thing. So this is going to become whatever minus 9b1. So that's going to end up with this being, I don't know, minus 0.5 or something. So now row 3 will never get touched anymore. Row 3, you have fixed all the entries. And now you go to row 2. So this you will replace this with 4 times b1. And that will ensure that this becomes 0.5. Okay, you need to do this in a systematic fashion. I'm glad Varun pointed this out. So you need to sort of start from the last row and start from the rightmost column and start fixing from there and then proceed upwards. Okay, so anyway, so what I'm trying to say is that so far the part of the algorithm we have come up with is just the following. We'll do Gram-Schmidt, okay, which is the standard Gram-Schmidt, but use this as a guide. And once you get m times b star, you try to round off m as best as you can. Okay, so now you will end up with a different, I don't know, m prime times b star equals b prime or something, which is this rounded off basis, because at this point, the basis has slightly changed. Whatever basis you started off with, you now have a slightly different basis. Okay, they of course still span the same entries. I mean, sorry, they still span the same lattice, but it's a different basis nevertheless. Okay, but the only thing you're guaranteed at this point is that now this m prime is made up of all entries which are within plus half and minus half. Okay, then what? So, I mean, often it might seem like, you know, okay, let's just do this. Let's just get the smallest vector we have and hope that this works. And this just fails badly. Okay, this alone is not enough. So now what I will do is I'll just tell you what the LLL algorithm is, which is more or less this, but it's like one very, very important step in this algorithm, which is going to make, which is also what I like the most about this algorithm. Okay, so here is the LLL algorithm. This is the Lenstra-Lenstra-Lovasz algorithm. And you know an algorithm is cool when it promises to be a polynomial time algorithm, but begins with while true. Okay, so at some point we'll have to convince ourselves that this will not just terminate, it will actually terminate in polynomially many steps. Okay, so the first 2 steps are basically what we have discussed so far. You do Gram-Schmidt and then you do the rounded off Gram-Schmidt to get the basis B. Okay, so far so good. I mean, you basically now have an equation of the form m times b star equals b, where b star is the Gram-Schmidt vectors and b is the basis that has now been slightly modified. And the guarantee you have right now is that m is a lower triangular matrix, all of whose off-diagonal entries are between plus half and minus half. And then you do this magical step, and this is called the Lovasz step, okay, which is the following. You check if there is any index I where some stupid inequality is satisfied. Okay, I will demystify this inequality soon. Okay, but this is something that you do. You basically, okay, right now you have a bunch of Gram-Schmidt vectors and see if the Gram-Schmidt vectors satisfy a certain property. And if they do, you just swap bi and bi plus 1. Obviously, the lattice is not going to change, because like swapping, I mean, changing the order of the bi's is not going to make a difference. But notice that the Gram-Schmidt algorithm is very order dependent. Right? The way you construct your Gram-Schmidt vectors, if I gave you a different order of the vectors, you might come up with a completely different Gram-Schmidt basis. And this is going to exploit that. So it's basically going to figure out whether swapping is going to be helpful in some sense. And if it decides swapping is going to be helpful, it will swap and repeat the whole process again. Like compute the Gram-Schmidt under the slightly different order, round off as best as you can, and see if there is any coordinate where there is some progress that you can make. If you can, swap it again. You keep doing this again and again. At some point, you might end up in a situation where all your Gram-Schmidt vectors satisfy this inequality with whatever, less than or equal. And at that point, apparently you just output B1 and say that's a short enough vector. Okay, is the algorithm clear? I mean, I'm obviously not going to ask if the correctness or anything is clear. It's an extremely mysterious algorithm. This just seems like a bizarre statement to check, but just bear with a little bit and it will really make a lot of sense as to why exactly this particular check.
Sir?
Yeah?
So are you saying that if we change the ordering and take different Gram-Schmidt basis, so might happen that the first trial, whatever basis we have, still that is for each is +1 -½
Sorry, I couldn't understand your question.
So I'm trying to say that if we change the basis, if we change the ordering, the Gram-Schmidt process, we might get a better approximation to the lattice, towards the lattice point. Is it true? Or it might happen that whatever way you are doing, the error that is from the nearest lattice point for each vector will be the same.
No, I mean, we'll make some progress, but it's exactly unclear progress in what sense. But I mean, at the moment, I don't want to think of it in the context of, are you going to get closer to integer points or no? There is a global reason that is going to help us make progress here. Okay, and it's not something as local as saying every time you do this, you get closer to a lattice point or something. But something else is getting better. And the whole algorithm is to figure out what that something else is and analyze that part.
Can you repeat second line where 3/4 you are doing? I didn't get that part.
I mean, at the point, I mean, I might as well replace this like some mumbo jumbo. I mean, it's like you're doing some step after which you're deciding whether you want to swap BI and BI plus 1.
No, what's this? I mean, maybe. So what's it saying in English? Like it's saying, so B star is what is capital B star? It is the current.
It's the current Gram-Schmidt vector. The ith Gram-Schmidt vector is Bi star, and I plus 1th Gram-Schmidt vector is Bi plus 1 star, and so on. And mu I plus 1 comma I are the entries of the matrix M that you currently have. In some words, it's saying, look at a particular vector and see if it is substantially smaller than your ith vector. If it is, that is by substantially smaller, I mean it's smaller by a factor of 3/4. If it is, then there is some reason to expect that swapping is helpful. Okay.
Why is that 3/4 term?
Yeah. I mean, like you can ask why this. I mean, there are plenty of whys we can ask. Let's slowly figure out. Maybe it'll start making sense once I tell you exactly what this vector is and why exactly you are doing what you're doing. Okay. So maybe a simpler question to answer is the following. At some point, we are going to end up returning B1. Whenever we do. Why is that a good thing even? Okay. So here is the first, this is a claim that I want to make, which is that when we do decide to return B1, I want to claim that this B1 is actually a very, very good approximation to the optimum. That is, it gives you the guarantee that you want to have. Oh, sorry, I missed a square. Okay, so let's just see that. I mean, like we'll figure out exactly what this equation is, etc. But let's at least convince ourselves that whenever the algorithm does return a vector, it will return a vector that is not too far away from optimum. Okay. Now let's just look at that equation. What is that? When will I end up returning B1? if it so happens that all of these inequalities are actually in the other direction. Okay, so let's just write that down. So this basically says that 3 by 4 bi star squared is at most bi plus 1 star plus mu I plus 1 comma I bi star squared. Okay. Now Pythagoras theorem on the right hand side will tell me that this is exactly equal to the norm of bi plus 1 star squared plus mu I plus 1 comma I squared times norm of bi star squared. What do I know about this? Mu I plus 1 comma I was somewhere between plus half and minus half. So therefore, this is somewhere between 1/4. I mean, it's no more than 1/4. Okay. And there is a 3/4 on this side. So which basically will tell me that the norm of bi star squared, half of it is at most the norm of bi plus 1 star. Okay, so I'm going to write this slightly differently. I'm going to basically say this is at most twice. Okay, so since this is a fact that is true for all I going from 1, 2, 3 all the way till n, what you therefore have is that norm of b1 star squared, which note this was equal to the norm of b1 because b1 star is equal to b1. Okay, this okay is at most twice norm of b2 star, blah blah blah, at most 2 power n minus 1 norm of b n minus 1 star. I mean, I'm just stringing together the equations that we have currently. So far, so good. Okay. Now, turns out in much of lattice theory, a bunch of basis vectors that satisfy this property also has a name. It's called a reduced basis. Okay, but I mean, ignore that for now, because we eventually want to figure out what happens to the optimum. Like, how can I somehow relate the optimum's length to the length of B1? And this is going to be very similar to what we had done earlier. So suppose B opt was the optimal vector. This is the shortest vector that you have. Okay, what does this mean? This can be written as some summation alpha I bi, where bi was the original basis vectors and all these alpha i's are integers. Okay, so I'm just going to write something here, but so suppose this look like alpha 7 b7 plus a bunch of higher terms, higher indices. That is what I mean is the first I for which alpha I was non-zero. Let's say that was 7. And from that point on, you got something, you know, yeah, you got something smaller. In fact, I would prefer this to write it in the other direction. So let me say, without loss of generality, let me write it as alpha n times bn plus lower indices. And I'm assuming that alpha n, this is not equal to 0. If not, you will look at whatever is the highest index that shows up in this summation. Now, I already know that each bn can be written in terms of these bn stars in some way, right? I mean, there is some particular doing it that way. So if I were to write it in terms of bn stars, so I'll end up with something that looks like alpha n times bn star plus a bunch of lower terms. Okay, and let me put a prime here in the sense that the lower terms could all potentially change. But here is the key point. I claim this is still going to be equal to alpha n. That coefficient would not change. Why is that? Notice bn is equal to bn star plus a bunch of lower order terms. That is, the diagonal term is equal to 1. So when I write bn in terms of bn stars, I will get one contribution of bn star plus a whole bunch of lower order terms. So most importantly, this coefficient would not have changed. Okay, so what I mean by this is, suppose this was of the form plus alpha n minus 1 bn minus 1 plus blah 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 blah. So now when I replace bn by bn star, by that what do I mean? I am basically going to replace by bn star plus some mu into bn minus 1 star blah 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 blah. Okay, so therefore the leading term is still going to be alpha n times bn star. Plus, I might have messed up all the lower order indices, but I don't care about this. Okay, so all I'm saying is that this looks like bn star plus lower order terms. So what does this say? Same proof that we had last time. This says that if I look at the norm of b opt squared, this is at least as large as alpha n squared times the norm of bn squared. Okay, which means it's at least as large as the norm of bn star. Okay, and this is just a different way of saying is that b opt, whatever this length is, the length squared, is at least as large as the length of the smallest Gram-Schmidt vector. But I know for a fact that whatever is the smallest Gram-Schmidt vector, b1 is no more than 2 power n minus 1 times that vector. But sorry, 2 power n minus 1 times the norm of b1 is at most the smallest bn star. I mean, that's what this reduced basis tells you, right? Okay, so the smallest, I mean, like the whatever this vector b1 is, it's no more than a factor of 2 power n away from whatever is the shortest vector that you have here. So this basically tells you that had I returned b1, I'm certainly within a factor of 2 power n minus 1 of whatever the object was. Because I'm returning something that is guaranteed to be no larger than 2 power n times the object. Oh, sorry, did I mess this up? Sorry. I should have probably written this should have been 2 power n minus 1. Right? I mean, like b1 is, I mean, it's certainly no more than 2 power n minus 1, the smallest. But I know that, therefore, I am certainly smaller than 2 power n minus 1 times the optimal. And that would at least tell us that when the algorithm decides to output something, it's at least outputting the right thing. It's outputting something that gives you the whatever guarantee that you have. But it doesn't, I mean, the next question should also be, what is that step? Like, why are we doing whatever it is that we are doing? Why are we doing this random swap business? Because we somehow need to argue that this swap doesn't like go on forever. Like at some point it stops, not just that it stops in polynomial steps. Okay. And here is the key point, which is what we are going to do is we're going to try and understand what happens to Gramschmidt if I swap two coordinates. Okay. So let's say B1, B2, B3, B4, B5 were my original set of vectors. Now I have this new set of vectors B1, B2, B4, B3, and B5. So I've just swapped 4 and 3. And I want to know what would really change in the Gram-Schmidt vectors. Like, what can I say about it? So maybe for this, the Gram-Schmidt vectors I got was, of course, B1 star will be equal to B1. There's no surprise there. Now I'll get some B2 star. I'll get some B3 star, B4 star, and B5 star. And maybe here I will get some B1 hat, B2 hat. I'm just going to put B3 hat here, B4 hat, and B5 hat. And I would like to know, well, which of these things are actually equal? Okay. Now, something that is obvious is that this must certainly be equal to this, because they're all equal to B1. And this must certainly be equal to this, because at this point, there has been no change in order. So why would you expect the Gram-Schmidt algorithm to do something different? Okay. I mean, of course, here this is an orthogonal component of B3, whereas this guy is an orthogonal component of B4. So there is no reason to expect that these two are going to be similar. Okay. So this, of course, I mean, I sort of expect them to not be equal. Similarly, this also I expect them to not be equal. And it's easy to somehow imagine that these two will also be not equal because, I mean, some change has already happened. So most likely the Gram-Schmidt algorithm at this point will do something completely bizarre. But here comes back the observation. What exactly is this geometrically? B5 star is nothing but the orthogonal component of B5 in the space you have so far. The space you have so far, whether you're looking at this or this, is the same. And the vector you have currently, whether you're looking at order 1 or order 2, is also the same. And therefore, the component will also be the same. The space is the same, the vector is the same, so the component will also be the same. The expression looks different, but it will actually be the same. You actually end up computing the same vector. So it turns out this is also equal. So if you swap I and I plus 1, the only thing that happens is that the ith Gram-Schmidt vector and the I plus 1 Gram-Schmidt vector will change. But the rest of the vectors turn out to be the same. Okay. Now that we know it changes, we can ask precisely what is this new vector. So what is B? Okay, let's look at what is, let me write down what is B4 star. What property did it satisfy? Let's just write down the equation so that we get familiar with this. So this is going to be B4 minus mu4 3 times B3 star minus mu4 2 times B2 star minus mu4 1 times B1 star. Okay. Now, what can you say about whatever this B3 hat? What will this be? At this point, I basically need to look at B4 minus something involving the previous two hats. Okay, so what is that going to be? So this is going to be B4 minus something times B3 hat. Sorry, something times B2 hat minus something times B1 hat. Okay, but I know B2 hat is equal to B2 star and B1 hat is equal to B1 star. Okay, so therefore I might as well replace this with stars. Okay, what should this be? So this should, I mean, this, whatever the constant that's here is to make sure that B3 hat's inner product with B2 hat is 0. Right? If you calculate exactly what this is, this will precisely be mu4 2.
That only depends on the vector you're taking and
Exactly.
what you want it to be orthogonal.
Precisely. And similarly, this will also be mu4 1. Okay. So now, what is B3 hat in terms of B4 hats and so on? B3 hat, this is nothing but B4 star. And the only term that B4 star in addition subtracted off was this one term, which was not present here. Okay. So therefore, this is just going to be this plus mu4 3 times B3 star. Okay. Now, does this look familiar? Okay, this is what's the right-hand side in the Lovasz step. So another way of stating this is the following. Okay. So if I end up swapping 4 and 3, the third vector will now be B3 hat. Okay, but if I didn't swap 4 and 3, the third vector is B3 star. And what we are asking is, does swapping I and I plus 1 result in a dramatically smaller ith Gram-Schmidt vector? You're basically saying, is B3 hat like smaller than, I don't know, 3/4 the mass or 3/4 the length of my old whatever B3 star? So then we are somehow saying that then it seems like making the swap is suddenly making the Gram-Schmidt vector substantially smaller. So let's make the swap and continue. Okay, so that's another way of reinterpreting what Lovasz says. So you could rewrite this algorithm to basically say, swap I and I plus 1 and do Gram-Schmidt. If it so happens that the ith vector is substantially smaller than the old ith vector, by that I mean it's smaller than a factor of 3/4, then this swap is useful. So do the swap and proceed. And you keep doing this as long as there is a useful swap to do, you do that swap. And you're somehow hoping that because you're making some Gram-Schmidt vector smaller all the time, hopefully there is some global progress that you're making towards coming up with smaller and smaller vectors. That's the rough intuition. Okay, so now I hope that at least all the parts of the algorithm is clear. Now the problem comes down to analyzing why does this algorithm terminate in polynomial steps. So are there any questions so far? Okay, so if not, let's just proceed. So right now we know that the Lovasz step, the mysterious Lovasz step, was basically saying, does swapping I and I plus 1, does it make the ith Gram-Schmidt vector substantially smaller? If it does, swap it and go ahead. If not, if it so happens that none of the swaps help, turns out B1 is already a good enough approximation, so you can return B1. Okay, good. So now we want to sort of figure out, why does this algorithm terminate in polynomial many steps? And in often cases, whenever you have an algorithm that appears to run an exponent, I mean like sort of run forever because there is a big while loop, and you somehow want to say you're making progress, much of it just boils down to finding a suitable potential function. You somehow want to come up with some potential function and somehow say that this potential function is going to tell you that the algorithm terminates in, I don't know, certain number of steps or something. Okay, so what we are going to do is the following. We are going to find a suitable potential function which depends on the basis vectors b1 through bn that we have. Okay, and we are going to do the following thing. We're going to somehow argue that whatever this phi is always an integer. And every time you do a swap, this integer reduces. Okay, I mean it's a positive integer, and every time you do a swap, the positive integer reduces by some constant factor. And we will say at the beginning phi wasn't too big. So how many times can you keep on doing the swap and reducing the integer? Because I mean there's only so many times an integer can become smaller and still remain positive. Okay, so that's going to be the rough idea. It's just coming up with the right potential function.
Like a sum of norm squared or something like that.
Excellent. So we're going to do something similar. We're just going to take the product. It's just because it's easier to analyze. Okay. So I'm just going to say B1 through Bn was my basis. The Gram-Schmidt vectors, the length somehow seemed to be the relevant thing because we were doing a swap because some length went down. Okay. So let's just take our potential function to be the product of all the length squares. Okay. First thing, why is this an integer? So these are the Gram-Schmidt vectors. So it's not the original basis vectors. So I somehow need to argue that the Gram-Schmidt vectors is also an integer. Okay. So can I write this expression in terms of the matrices somehow?
Can you go to the process?
Sorry, which process? The Gram-Schmidt process.
Yes, yes.
Yeah. So this is what you in general have. You have an equation of the form m times b star equals b, whereby which this b star refers to putting all the things as rows. Okay. Suppose you looked at b star transpose. What would you get?
I'm just confused somehow.
Uh-huh.
Why
Uh,
you choose the product? Means is there any logic for that or something?
I mean, basically because we just argued that the reason we did a swap was because the ith vector came down. That vector reduced in length. So you somehow, I mean, you can take the sum also. It just so happens that the product is slightly easier to analyze.
Means is it a combinatorial problem that there will be a finite number of steps where every vector can be reduced up to some length, at most some length one or
I
something?
mean, right now, all we are doing is we are trying to come up with some potential function. And I would like to argue that it's a positive integer and that every time we do the swap step, this potential function becomes smaller.
But is your previous method guarantees that this potential function exists at all?
I mean, what do you mean the potential function? I'm just defining what the potential is. What do you mean by that?
I mean to say that it might happen that if we do two swaps, it might happen that the ith vector again gain the weight, gain the height.
So we'll have to argue this because right now we know that after doing one swap, there are only two Gram-Schmidt vectors that can change its length. If I swap I and I plus 1, the only thing that can happen is that the ith Gram-Schmidt vector and the I plus 1th Gram-Schmidt vector, they could now be different. But otherwise, everything else is the same.
Yes.
Right? And since it is the fact that the ith vector seems to have gotten smaller, because that's the reason you did the swap in the first place.
Yes.
So it seems like this is a reasonable potential function. Okay.
So in that procedure, wait, but the I plus 1 method,
yeah, I plus 1 vector,
right?
We'll see. Hold that thought, which is why this is an attempt and not the answer. Okay, so the easiest way to look at this is that you look at B star and B star transpose. What is this matrix going to be? I mean,
in 0, 1.
Sorry?
Some matrix in 0, 1 means identity.
Not quite. This is B1 star, this is B1 star. So the whatever, the 1, 1th entry is just the norm of B1 star squared. But it's orthogonal to everything else. So basically you will get a diagonal matrix where this is like Bn star squared. Everything else is going to be 0. So this is just B star and this is B star transpose. So therefore, the determinant of this guy, this is equal to the potential function we care about. Right?
So determinant of B star square equals to 5.
Yeah, the determinant of B star squared equals 5. But I also know B star in terms of B. Because this is nothing but, I don't know what, M inverse times B transpose times M inverse transpose. That's the same thing, right? Because I know B star, I mean, M times B star is equal to B. So therefore, I can write B star in terms of M inverse, whatever. But what do I know about this matrices M? There were lower triangular matrices that had 1s on the diagonal. So they have determinant equal to 1.
I mean, doesn't matter. When you are taking determinant, they will cancel out.
Yeah. So therefore, determinant of this is the same thing as equal to determinant of BB transpose. Fortunately, this guy is made up of integer entries because this is the basis we started off with. So determinant of B star transpose is equal to the determinant of BB transpose, which is equal to the basis that we started off with. So therefore, that is certainly an integer. Okay, so great. We came up with a potential function. Sorry, I might take about 5 more minutes. So we came up with a potential function. Turns out it's an integer. Fantastic. Let's just proceed. But this probably already, seems to be putting a nail in the coffin. So by the way, this also tells us that the number cannot be too large to begin with. Because in the beginning, I was given some bunch of basis vectors. I am told every entry is like at most this much or whatever. So it'll be some, I don't know, it'll be some n cross n matrix where all the entries are at most, I don't know, 2 power c or whatever. So you get some stupid bound. So it also tells you that your initial value of the potential function is not too large. And here comes the tricky step. Why does phi keep reducing after every swap step? Okay. And we said, we know bi star reduces, or rather whatever the length of this, by a factor of alpha, which is certainly smaller than, I don't know, 3/4 or something. Because that's why we did the swap step. We said, does doing the swap make the ith Gram-Schmidt vector smaller? So the question is, what about bi plus 1 star? So Varun was asking, does this increase or something? Okay. Turns out it does increase. Okay. And by exactly 1 over alpha factor. So whatever gain you got in the ith vector, the I plus 1th vector will just completely undo that gain. And in fact, the proof of it is just above. It basically says what's the length of the, what is the product of the lengths of all Gram-Schmidt vectors? It's this determinant. Now, obviously, if you swap I and I plus 1, this determinant stays the same. So of course, phi is also going to stay the same. And the worst potential function in an algorithm is an invariant, because it doesn't change at all. Right? So this is a weird thing where our phi that you're working with is actually turning out to be an invariant, and it's not the right potential function we want.
Now I got what you meant when you said nail in the coffin.
Yeah. Okay, so this is the, so now there is one final trick, which is you do this. Okay, you look at the sum, the product of all prefixes. That is, you look at b1 star squared times b1 star squared, b2 star squared, times b1 star squared, b2 star squared, b3 star squared, etc., etc. So if you basically multiply this all out, b1 star shows up more times than b2 star, which shows up more times than b3 star, etc., etc. Okay. Now, why the hell is this an integer?
There's one alpha factor extra that you said whenever.
Yeah, that's what is going to save us eventually, to say that this one reduces.
Oh, but why is it an integer?
But why is this an integer first? So can you somehow prove to me that this is an integer?
So while we are doing the Gram-Schmidt process, there is always, we are dividing by some vector, right? U minus some norm of u.
Yeah.
So I think that will cancel out with the highest power of.
Sorry, I didn't follow what you mean.
U minus some alpha and u I minus some alpha summation alpha I into ui, right? I less equals to u I plus 1, right?
Okay.
So that alpha is the coefficients are in the fractional form.
Yeah.
In the lower part of the fraction is each of the norm vectors, some norm of ui uj. So will that cancel out?
So I don't see how to work with that, because I mean, everything else in that Gram-Schmidt expression, they're all orthogonal, but there is also one unorthogonal ui. So I don't know how to deal with that in particular. But the proof of this is exactly the same.
I mean, there's just the upper part of that.
Precisely. Right? So all we are saying is, like, you look at B star and B star transpose, but only look at the first I rows. Okay, if you just look at the whatever a rectangular matrix, which is bi star whatever, and this other rectangular matrix, what will you now end up with? You will now end up with an I cross I matrix, which is b1 star squared and bn star squared. Okay, and fortunately, this is again equal to the following. This is this M inverse, but B only the first I rows, be only the first I rows. Sorry, this is transpose times M inverse squared. And you now need to argue that the determinant of this still makes sense. It's a square matrix and the M's don't really bother. Because it's like you're doing a similar matrix or something of that sort. I mean, this requires a little bit more thought. I will let you think about it more. But it's basically the same proof that will tell you that each of these, whatever subproducts, are all integers themselves. And therefore, this entire thing is also an integer. So again, the same thing works. This potential function is currently an integer. You can also argue that initially the value is not too large if you're depending on what the input length was and something. And now, most importantly, you can now argue that now this goes down by a factor of 3/4. Basically, because bi plus 1 reduces by 3/4 in length. And sorry, bi reduces by 3/4 in length. Bi plus 1 increases by 3/4 in length, or increases by 4/3 in length. But fortunately, the lower guy appears more often than the higher guy. So then you have a net contribution of 3/4 from every swap step. Okay, and that's it. And this basically will tell you that the algorithm terminates in poly in many steps. Because you know your potential function was something that looks like 2 power order Cn to begin with. And I'm telling you that every swap reduces by a factor of 3/4. So it can at most reduce by logarithmic in the initial value. So it stops in polynomially many steps. Okay, so let me just keep this, which is the final, just a theorem statement, which is the Lenstra-Lenstra-Lovasz algorithm, which is that you can get a 2 power n minus 1 by 2. The by 2 only comes from the fact that I think we wrote it in terms of bi squareds. Whereas when you're looking at the length, it is like 2 square root of that. So you get a 2 to the roughly 2 to the n approximation to the shortest vector problem in a lattice in polynomial. And if you take this subroutine, plug it into the integer factorization algorithm, you now get a polynomial time algorithm to factorize integer. To polynomial time algorithm to factorize polynomials over integers. Yeah. Okay. It's a. I hope I did some justice to the algorithm. It's one of the coolest algorithms I have seen ever. It's not hard at the end of it. It's basically just Gramschmidt. There's nothing else that's really going on, but it's having the right geometric view of what Gramschmidt does, and something that you don't think about at all. Like in the sense that even though Gramschmidt is about getting an orthogonal basis, this question is very order independent. Because it feels like, okay, you have a basis, you want to find a different orthogonal basis or something. But the algorithm is order dependent. And it's one of these things that actually exploits the differences in what happens on Gram-Schmidt when you change the order. So it's a pretty clever algorithm, and the analysis is also quite clean. Okay, so this is the, I don't know, in my opinion, the final peak I wanted to reach in the factorization part of the course. I would like to conclude the polynomial factorization part of this course. And from the next lecture onwards, we'll start proceeding towards operations on integers and also deal with, there also factorization will play in, but now it's going to be factoring integers. But we'll start with some more basic stuff and then build towards that. We won't be doing a polynomial time algorithm to factorize integers. But, yeah. Okay. Sorry for taking more time today. And whether or not we are going to have a class on Thursday, let's discuss that on Academy. And then we'll see when to have our next class. Okay, great. So let me stop here and